For those of you that have not heard about Bernie, shame on you. He's very well known in the modeling and simulation community. He's been extremely active since the 70s when he defined a new theory of modeling and simulation that was revisited since then. It has evolved, improved, increased its reach. The foundational book on theory of modeling and simulation is going to have its 3rd edition really soon at the end of next year, right? 2018? Or this year? Early 2018, it's almost done, so it's a 3rd edition with the latest advances in the theory. Bernie has won every single award that you can imagine, ranging from Fellow of IEEE up to Inform's Lifetime Achievement Award, SCS Hall of Fame, and for his many contributions to the area of theory of modeling and simulation. It's really great to have you here, to hear you talking about your new ideas on why we don't have to develop a single model, but we have to develop them in pairs. So without further ado, welcome Bernie.
Thank you very much, Gabriel. Doing a sound check, it's good. And see, I see people still coming in, so I'll give a little time. No, after that tremendous talk this morning by Barry Nelson, I can say he more or less covered everything I would have said and left me about 1/50th of the talk to expand on. And when he talked about models of models, and in a sense, that's what I'm going to be talking about. And you may not like me after this talk because I'm saying instead of one model, you should be developing at least 2 every time you do any modeling and simulation. So maybe if I'm successful, you won't like me, but you've renamed the Winter Simulation Conference the Winter Bi-Simulation Conference. So maybe that's what we can look forward to if you agree with what I'm saying. So I'm going to try and sort of give you a panoramic overview. There are a lot of details that I could cover to make these points, but time doesn't really permit going into details and the kind of examples I'd like to show. But I sort of have them on slides, and we'll have to skip over things quite quickly. But like Gabriel said, a number of books are coming out. This Theory of Modeling and Simulation, 3rd edition, will be coming out soon, and it has a lot of this material. So, the conventional approach is, of course, to focus on a single and let's say, the pretty complex model that you're trying to capture, a system, or as Barry Nelson said, now a system of systems, and more or less follow a structured development cycle, somewhat like he showed that waterfall model that may or may not be followed exactly. So why should we put in twice the time and effort to develop 2 models rather than 1? Well, the short answer is that the extra effort we put at the beginning, may pay off at the end, just like most things that the greedy approach ultimately doesn't produce the best final result. But to give you a longer answer, I want to be able to show you, at least suggest or make the case that building, working with two models at least, this complex model that's, say, intended for the real solution, and a simpler model that represents, say, the best, I don't know, the most important characteristics of it for a particular purpose. That is best if you do it from the start. Often you have to, as you get into more complexity building the model, you realize that it's beyond your comprehension, and you need to simplify and work with some smaller representatives. And you realize that maybe later on when it's late in the process, and you're under stress to do something, get something done, and you don't really get the best results. So that's the idea. We want to be able to work with, say, a complex model and a simpler model, and there's some theory behind that that allows us to actually relate the two in sort of generalized ways and constructive ways. And that does lead to, as Barry was saying, to a multi-resolution family. It doesn't take much, once you start thinking in terms of pairs, it doesn't take much to go further, and you already have iterated kind of family of models. I guess the agenda for the talk basically is to convince you that approach is needed, whether you just think in terms of a single, complex model that's sufficient, or you recognize, in certain areas like combat modeling, like I'll try to get to, that when you're building these big simulations, you do need multi-resolution models. Paul Davis of RAND has focused and really put that point of view, made it central. So the agenda is that we should be building software tools, software and hardware, to implement the theory, to support people, modelers, simulation modelers, working working on pairs of models or multi-resolution families of models. So right now there's a lot of effort to do that. So we want to make that effort less onerous. And I'll try to, give you some details and examples. I do have them more or less sketched out on the slides. We probably don't have enough time to cover all of them, but also I plan to make a video of this presentation. I'd be happy to tell you how to get it. I'll put it on YouTube so it's available. And then try to summarize, make the points again. Okay, so it's hard enough to build a target model, and rather sort of quickly, what can a simpler model do? That was mentioned somewhat by Barry this morning as well. It usually can more easily give you insight into the important interactions, factors in the model. Because it's more abstract, it is probably more general, so covers a broader array of possibilities. And again, I guess keep harping back to what Barry said, because he said it so well. But that simulation should move away from a single instance of the real system as it is now to more the design attitude, design stance, where it's only one instance, one point in the whole space. So that really our models should be able to generalize to allow us to move out beyond the single point or the few instances that we're working with to a more general family of, in that same domain. It can be used to test the target with a more complex model, and that's a very important development that's happening with the use of model checking in simulation as well to develop models that are logically testable, but relate to the simulation model in the way we're talking about, that they represent some essential features of the model. It can proxy or substitute for the target, and that, often, I guess in the past you might say, with restrictions on the computation power available, you had to always think of more how are we going to fit this model into the available resources, and you wound up simplifying. And then you could say that was a target for the, or proxy for the target. But nowadays, there's other reasons, and I'll talk about one that, or at least mention one that has to do also with the machine learning that, again, Barry was bringing up. And which is, like he was saying, we've got to take that into account. We've either got to compete with it because it's become so powerful with all the resources it has, or use it. Use it wisely. And then there's also the idea that the simple model can explain the target's behavior better, especially to the user, to the customer, to others, than the actual target model, if it does represent truly what the target model is doing. But this all sort of comes under certain restricted conditions that allow you to simplify, and so that's kind of where we start going toward a theory, and I want to mention that to bring up these principles of valid simplification that really, when you look at what, again, Barry was saying, aggregation, disaggregation, and I'm going to call lumping, because you'll see in a moment, I mean, it's kind of a shorthand way to talk about it, that often what you're doing is taking advantage of uniformity or homogeneity in the things you're lumping together. Okay, so they have some kind of commonality, and it's a commonality that is operative in the it matters and sort of controls the output and controls what's happening that you're interested in. And so the conditions often boil down to having uniformity in the things that you're lumping together. But more than that, and this is probably less understood or less considered, is that when you're lumping these components or blocks or things together, the way they interact, okay, has to be in a form where the individual identity of the things being lumped doesn't affect the sort of lump-to-lump interaction. So the individuals in the blocks that are being lumped don't know the identities, don't make use of the identities of the other blocks, of the individuals in the other blocks. And that idea, it really turns out to be the justification for doing a lot of the aggregation approaches in simulation. So what I've tried to do over the years with theory of modeling and simulation is to formalize these basic ideas, just recognizing that valid simplification basically boils down to these requirements. Maybe you have a counterexample where simplification somehow doesn't boil down to this. I'd be happy to hear it, and maybe you haven't taken it into account, but I certainly claim that a large part of the story happens to do with this. So the formalization comes through systems, the idea of a general system or mathematical system, developed in the 60s. Wymore is one of the people known for developing a general simulation, or not general systems theory. And so first of all, lumping a lot of things together here in short, systems formalize simulation models. That's how I take it, that the general system concepts allows you to formalize to logically, mathematically represent what's going on in a simulation model. And then the idea of simplification is captured by the notion of system morphism, or a relation between a pair of systems that preserve certain properties, that preserves, for example, their behavior. So the idea that I've been working with for a long time is that system morphisms capture the requirements of uniformity and indifference. So uniformity, indifference, the principles are captured by system morphisms. And therefore, if you believe that the aggregation and so on, all the things that are going to be needed to deal with system of systems, as Barry was saying, boil down to doing lumping in the right way, you're going to have morphisms there to guide how you do it, to check it, to make sure it works. But the next point is these morphisms, or these conditions, on the face of it, you look at them, they're pretty strong. Uniformity requires all the components have the same structure, so that's pretty strong. And indifference would be the situation where they don't know, can't take account of the identity of the other individuals being lumped together. So those are fairly strong conditions. So what we really want to do, is what I'm claiming, is be able to have approximate morphisms, to have morphisms that capture the strong conditions, but then let them loosen up and allow us to understand how much we can get away with, how much we can relax the conditions and still get useful answers. So this goes back to maybe early on, like what a model is always wrong, but how wrong is it? So we want to be able to express and work with those in a daily manner. And that's the last point, so we need software tools to make these morphisms operational. And so I'm going to point out some initial developments that we're working with to operationalize these morphisms, these approximate morphisms. So we want to develop principles for constructing base lumped model pairs. So what I call, complex simple, I like to think in terms of base lumped. So there's a base model, let's say the target model, but it's a more complex model, and a lump model which is aggregated or some form simplified. We want to develop software tools for testing morphisms, especially approximate morphisms. And these tools should be broadly applicable, so they should not be dependent on domain. They shouldn't be domain specific, they should be broadly applicable to all domains, just like systems. The idea of general system was that there are certain structural properties and behavioral properties that cut across the systems or in our case, the simulation models that are developed in different domains. That models of all domains have certain properties that are useful, and the same thing we want to say for the software tools and for, of course, the morphism concepts. So if we can reduce the additional effort to work with the pair of models approach, then maybe in 25 years we'll have a bi-simulation conference. That would be a good result, or give it a name, but maybe something that recognizes we're dealing with not just single simulations at a time. So here's some graphics to try and give you a picture. We have a base model which has got components at the top, and you block off components, into blocks. And so here we're blocking into 4 blocks. And the base model is an interaction of these finer grained components. And the lump model has lumps these together. And we want to have the ability to work with the mapping that does this lumping. But it's not far to see. Like I said, it doesn't take long before you realize, well, you're really talking about a multi-resolution hierarchy, because the base model could itself be a lump model for another base model, so you have to introduce more complexity for some reason. Or the lump model, the base model could itself be inserted as a component into a model like system of system, which the base model is one component of one system. Now you have a system of systems. So it's not hard to see that there are base models all the way up and lump models all the way down. So really we're talking about a hierarchy or a multi-resolution family. So there are examples that I'd like to talk about. I know there won't be time, so I'm going to try to sort of go over quickly and try to pull out their main points. One thing is brain simulation modeling. I'll focus on that, just like as the main story. And combat modeling, where there's a history of multi-resolution approaches, because that's an area where wargaming, simulations, complex simulations had to be developed for training and so on, where the multi-resolution idea sort of had to come about, as I mentioned, pushed forward by Paul Davis at Rand. Then, to illustrate the idea of, let's say, components interacting where the identity doesn't matter, but still tells you a lot, I'll mention the multiprocessor speed up issue. This is Amdahl's law. Amdahl's law states that you can get an n-fold speed up when you have n processors. The idea, though, is that sort of says that the processors don't take advantage of, or there's no effect of identity in the interaction, especially in the interaction here where it's going to be with the communication medium. But if you do allow that interaction, sort of what happens? What's the story there? And finally, I mentioned this earlier on, the machine learning. So a little background, the company RT-Sync is a spin-off of the University of Arizona, the Center for Integrated Modeling and Simulation, where I was for many years. And we're working on a STTR, a technology transfer research, that has to do with missile defense. So there is an area where you can't really test missiles. You can if you're in North Korea. But more than that, you can't test numbers of missiles, raids of missiles, or whole sets of missiles operating together. You have to go to simulation. So that's why the Missile Defense Agency spends a lot of money. And we found that we had to develop a simplified model of the data produced by the simulation to support the development of a machine learning or AI classifier for the scenarios that we're trying to classify. So before being able to generate the data for the design, like Barry was saying, it's in the future, you don't have the data available. You have to guess what it's going to look like. And this is another instance of where the idea of simplified or models that allow you to substitute for the target come in. This was a new sort of idea for us, and it's not fully formalized, but I wanted to bring it up as, there may be many other areas, many other problems that require the kind of approach I'm taking here. So to sort of organize this area, maybe it's a new area, pairs of models approach. I have a taxonomy just to sort of lay out the ideas. First of all, which model are we talking about, base or lump model? What kind of model behavior generation are we talking about? So, simulation is a focal interest here. But in the past, the alternative was analytic, let's say, mathematical, applied math approach to characterize some aspect of the model. But now we're seeing more and more, as I mentioned earlier, logic-based models that represent the behavior, but often in a form like not as complex, where the timing is not as well brought out, simplified. So these are logic-based or model checking kind of models. And then we can have which direction are we talking about? So I mentioned that the lump model can test the base model, can do checking of the base model, but you could also have the base model checking the lump model, because you've developed the base model to some extent, or maybe a large extent, and you want to develop a lump model for some reason, like we just, many of the reasons, and you want to make sure the lump model represents the base model properly, so you want to use the base model to check the lump model. So the direction can go either way. And I just want to bring out a taxonomy like this, formalized in some way. What I was trying to convey is that the base lump model pair may be very fundamental to our whole enterprise. Okay, thinking of two models rather than a single model may be the essence, if you like, of our simulation work. And then the question, it's very important, what question are you addressing in making a simplification? A simplification will work for one issue or question or purpose, what I call experimental frame, and not necessarily for another. So it's very important to have that in mind. So, here's some possibilities. The lump model is analyzed to check the base model. That would be the classical applied mathematics. The lump model is simulated to replace the base model to address the same question of purpose. That would be what was typically the case, maybe is, of course, the case, that we have to get away with a model that consumes less resources than we would like. And then the base model is simulated to check the lump model, just as I mentioned. And in these examples, they each sort of illustrate this, the roles that I've just pointed out in the taxonomy. So I won't go through it, but you can look at examples and see the way these roles are played out. So, getting now to the conditions, we said the uniformity and indifference. Okay, so I'm going to do this one example with neural net to illustrate that, and maybe it's an interesting example as well, in one block. But then we can have the uniformity and indifference in two blocks, and that's in this combat modeling where you have a red force against a blue force, and you're looking at the attrition in each one as time goes on. If you assume that each are homogeneous, and you also have to now account for their interaction through firing at each other, which needs to be indifferent, as I said. And here you get a very distinct view of what that means. Then you can get a lump model, which is what they often use called the Lanchester model. So, but then what if they're not satisfying those conditions? So how can you deal with that? Well, that is now the approximate morphism. And then the multiprocessor example has the processors all of the same kind and interacting through a queue representing the connection, the network, connecting network, and interacting with it in a standard way. It doesn't know what identities there are, but if there's priorities on the processors and their interaction with the network that, some have higher priority than others, then you go to the non-uniformity. So now the indifference condition doesn't hold, and the question is, how do you deal with that? So just try to illustrate to you that these conditions come up, and now we need ability to deal with them. Okay, so Gabriel, how much time do I have? A few minutes? 15, okay. So in 5 minutes, I'm going to try to do this exam. Yeah, in 5, and I'll leave 10 for, okay. So I think hopefully this is sort of interesting. If you take the current situation in brain modeling and simulation, the Spinnaker people, Ferber, Stan Ferber, C. Ferber, and others, but they're trying to build a computer, a parallel processor, okay, that has enough neurons, simulated neurons, if you like, to match that of the human brain. Okay, so the human brain has around 1 trillion neurons. But right now, their Spinnaker architecture is at the level like they can do 100,000 neurons, okay? So it's still far away from the trillion. So we could ask the question, something about what the Spinnaker or the highly complex brain model would do, even though we can't simulate it right now. And we could ask, how big a model do we need to answer some question about that unrealizable simulation? That is a burning question for these kind of modelers. The question, if we can't do a trillion neurons, well, how many do we need? Will 100,000 work? Will, 1 million work? So for one question, as I said, it will depend on the question. Obviously, we try to simulate everything a human does. I don't know, obviously, but I don't think you can do it with 100,000 neurons. So one question is that it works out, that you can answer the question that I raised, is you want to know for a particular neuron model, you have that in mind, the component, the neuron, and certain connectivity, how they connect. What would be the steady state firing level? If you ran this model long enough, what level of firing would it get into? That by itself is an interesting question. It's not sort of trivial because brains can easily get out of sync, out of stability, go unstable. When you get epilepsy, things get out of hand. The firing goes too high. Okay, so you want basically a requirement on any kind of neural net that represents the brain. We're not talking about deep learning where there's no dynamics to it. Here we're really having the things interact. What level of firing would result from a certain model with certain connectivity? So we want a model that can be simulated and whose rate of firing would predict the full-scale counterpart. So let's make an analogy to aeronautics. where it's long established that you develop a scaled airplane and you put it in a wind tunnel and you get certain results for the drag and the other factors, and then you can scale back up and say the real system, the real airplane to be designed, would have to have this kind of form, or take on this kind of design. So that is an instance of a base lump model paradigm. And can we apply it to neural networks here, to real neural kind of networks, not, let's say, deep learning type. So here's the approach. We can't, we have the real neural cortex. We can't construct the real, or one that has the same number of neurons and the same connectivity, but we can do a scaled version of it, which is the lumping process, which we can feasibly simulate, or we're asked the question, can we feasibly simulate it? And if we can, we get some results, and we infer back those results to what would happen if we could do the whole Spinnaker goal real network. So it turns out, with this approach I'm talking about, with the same model of the neuron, the average number of neighbors must be kept the same while drastically reducing the size of the net. So it turns out that with assuming this uniformity condition, the indifference in uniformity, that the only thing that matters for a neuron is the average number of neighbors, the average number of inputs it gets, or other neurons that are sending it inputs. And if you keep that the same and reduce the number, you can get the same steady state firing. So the smallest scale model that you can have is then a fully connected net where the size is equal to the average number of neighbors plus one. So in other words, you just make everybody connected to everybody else, and each one has the same number of average number of neighbors. So that's a scale reduction of 10 to the 11th down to 10 to the 7th, because 10 to the 7th is about what the connectivity is for neural nets. So I have some quotes, some references for that if you're interested. But then this 10,000 size net, which would, is feasible. We can do 10,000, but we would need 10 to the 8th connections. So we'd still need a lot of connections. Whether that's feasible, I don't know. Anyway, so viewed as a pair of models, we have a real system, which is a neural net, the real brain, a base model, which is the model that we construct with neurons, like a Spinnaker architecture, and the lump model that we make to represent it, but for the same experimental frame, which is that question of steady state firing. And just to quickly show you, what the reasoning is behind this. So on the left here we have the base model with a sparsely connected net, and I'm showing all the neurons are lined up together, one after another, so you can get a visualization of their input neighbors, their inputs. Then we have a lump model of the neural net itself, of the neuron itself, which is a Markov model in DEVS, discrete event system specification. And reasoning on that lump model, we come up with the conclusion that I said. But just to mention here, this is like what for physicists call mean field approximation, okay? But it goes beyond that in that it takes account of not just sort of a simple representation of a component, but complex Markov process representation of it. And then by the kind of reasoning I just said, we find out that the average number of neighbors is the only thing that counts. We can then reason that any neural net with the same components having that same average number, and the smallest one would have 1 plus that, will have the same steady state. And I've checked this not with trillions of neurons, but I have checked it with large numbers and small numbers of neurons to see that this prediction actually works. Okay, so give me again a count where I am. 5 minutes. So I'm going to skip over these examples. Here, quickly, in the case of combat modeling, you have like blue force and red force. You can relate the indifference and uniformity conditions to these two: emitted fire uniformity. Every unit distributes the same total fire volley to the opposing group, and received fire uniformity. Every unit receives the same fire volume from the other group. Okay, so you see they're not distinguished by the interaction. The individuals all sort of interact with each other in uniform ways. But what if those conditions are not satisfied? Then we back off from those, and now we're in approximate morphisms. And what we get from there is that we can say how far away can you go from these uniformity conditions and still get useful approximations. Okay, so you can draw a kind of graph conceptually like this, and you get a lumpability zone, a zone in which it's much bigger than the point, so the points that are required for the full conditions to be satisfied. You expand the zone out, but you can say how big that zone can be, and you can still get uniform conditions or satisfied conditions. And okay, the multiprocessor idea, you can get Amdahl's law, but taking into account the effect of communication speed on that. This is the example with the machine learning. We developed a model that allows us to test out the machine learning algorithms, to even develop them first, because you need to know what data they're working on, really. This sort of gets to what we can contribute to machine learning. We are the ones who can develop models of real things, and we can use them to test machine learning. Okay, so the multi-resolution families of models, I have an example with a global warming, which we've done, where you organize the models by the questions that they address, and then you have the model components and the approximate parameter morphisms. And now, as I said, we're developing software tools to test to represent the homomorphisms, the mappings, and to test them out. And sort of this is like by simulation, like I was saying. You work with two models at the same time. And you can develop simulators and approaches like this one, where you have a whole workflow that takes two models in and tests them and does it all sort of in a standard orderly way, you might say. Okay, so this is the conclusion. I've kind of stressed these points. And what I'm trying to tell you is let's all try to work on two models or families of models and start using systems theory and homomorphisms and morphisms, because maybe that's how we can compete with other disciplines and be around for another 50 years, like Barry Nelson has said we should. So I'll raise it for questions, disagreements, or whatever.
So we have a few minutes for questions. If you have a question,
I may have missed it, but doesn't the ability to lump or the characteristics of how much you can lump depend on what you're trying to get from the simulation model? And also, if that's the case, with the neural network model, what were the goals of the lumping?
Right.
What was the purpose of it?
Yeah, like I said, remember the purpose was in that taxonomy as well, right? So the lump model it relates to the base model typically only for a particular purpose that you already had in mind. And I call that eventually becomes the experimental frame, which is how the models are tested, or under what conditions you execute these models. How are you trying to answer the question? Okay, so it does depend, there's no question. In the case of the neural net, the question is, what's the steady state firing level? After you let it run for a while, how does it fire? Which could be, does it go unstable or not?
Thinking about how those different pairs can be dynamically controlled by yet another model.
Mm-hmm.
Is that
Can you give me an example of what?
For instance, going from a high resolution to low resolution model,
Right.
If there are some set of conditions that can trigger those switches.
Right. That's a good, many applications are of that kind. When you want to, let's say you run the high level model just at the beginning long enough to sort of get the basic components worked out. This is how they actually do it. And then once they're worked out, you use the lump model to take over. So yes, I mean, there can be dynamic control of the base and lump models, aggregating and disaggregating. It's in the DoD, the defense modeling community, this is kind of a well-known requirement that they work with.
So,
I think
come.
Axel, I mean,
Thank you, very nice presentation, and I agree with this necessity to address the various facets of simulation, because each simulation is just one viewpoint. And I think that introducing more viewpoints is absolutely essential to us to make progress. The challenge I see is whenever I think about isomorphisms and homomorphisms, I think about graph theory and computational complexity, and the problem that these are very hard to solve problems. How do you address this within your approach, that we may run into computational complexity issues when we in particular are interested to find out if two models are actually just different viewpoints, facets on a problem, or if they are actually conceptually so different that they are representing different states of minds of the modelers?
okay, you're certainly addressing hard problems, which morphisms or equivalence relations bring up. And it's sort of like, they get harder as you allow the representation to have less and less structure, okay? So if you have the components and their couplings and what's inside them, there's more constraint on what these morphisms can be than if you take that kind of model and represent it by a state graph and then ask how the two state graphs relate. So I work with a higher, more structure, because I think that's what simulation does, okay? We don't try to solve arbitrary NP complex problems. We try to solve real-world problems that, we sort of have an answer to already. The ones you're raising, are important, but they're also difficult. But I think we can make a lot of progress without always tackling them. They shouldn't be stopping us from doing anything. Yeah, there's one question here. I'll just. Yeah.
Very interesting viewpoint. How easy is it to actually implement in practice? Because I've built these red on blue models for combat, and I coded it up all myself, and there are a lot of sort of detailed structure and so on. Is there any hope that you have in terms of your approach that would make the process easier and allow you to actually construct it in a sort of pairwise method as you model as you're moving?
Well, I think you would look for where the uniformities lie, possibly, and take advantage of them, force them to exist. Okay, sometimes force them, and thereby derive some lump models, and then back off, and then allow the uniformities to come back in, and then you have the approximation morphism. I think that there's a really good account of these kind of models in the NPS, the Naval Postgraduate School. They have a nice description, and now there's a book out on combat modeling, I guess, that deals just with this kind of issue, these kind of issues.